complicated examples. That's just a few minutes to get the gears turning and remember how we think of this. What's the very first step that we do if we want to evaluate this integral? Right, so the first thing, which is not really, you're not doing any calculations or anything, but the way that we always have to think of this is that this is the limit as t goes to infinity, and we're integrating from 1 up to this new variable t we've introduced of 1 over x squared, which for the purposes of what's coming next, I'm going to write that as x to the minus 2. So we want to make this switch because we'll deal with the limit later, but now the t there is some number, and that is a setting where it makes sense to use the fundamental theorem. Infinity is not really a number that we can substitute in, so we don't want to treat it like any other number. Once we get here, this becomes a normal integral, or you do what you have to do to integrate it. In the labs this week, we're going to be doing more complicated integrals. Some of the ones we're seeing in class are ones where we basically know the antiderivative, but maybe you have to do a u substitution, maybe an integration by parts, whatever it takes to integrate that, go ahead and do it. In this case, this is a power rule problem. And so we still are carrying this limit around. But integrating this, the exponent increases to -1. We divide by the new exponent -1. And so that looks like, well, x to the -1 divided by -1. This thing we're evaluating from 1 to t. And as a step that I'll just do next, but this expression here, while having it as a negative exponent makes the power rule easier to see, because you really don't want to leaving it like this and trying to integrate it. There's a common mistake is just using a power rule on x squared and you just leave it in the bottom, and that's not how it works. But after we've integrated, when we're evaluating things, and especially evaluating the limit, having it as a fraction is easier to see where the pieces go. So this thing in here is -1 over x. So that's what I'll start substituting in. So after the integration, now we put these two endpoints in. So the limit as t goes to infinity, if we put t in, this just changes the variable to match the variable that we're taking a limit of. So we get -1 over t. And then if we put in 1 to this, we get -1, but in evaluating, we subtract. So we get +1. And now at the very last step, we're done with the integral. We just have a thing in terms of the new variable t and find a limit of this. And the 1 sticks around, the t in the bottom goes to infinity, so the fraction goes to 0. And so this is just 1. Questions about this problem, which is a sort of the no real frills version of what these improper integrals look like. So a question that, if you look back at what we've asked yesterday is, along with this example, is we've done a bunch of different integrals that basically look like this with different powers. So a question that we can ask and actually completely answer is this one, for which powers p does this integral, the integral from 1 to infinity of 1 over x to the p, converge or diverge? So we've looked at, I think, 3 different instances of this. So this is the case when p equals 2, and we did the calculation, we found that it converged. But what will be nice to have is, well, it would be nice to know just by looking at it and seeing what exponent do we have, whether it converges or diverges. If it converges and you want the number, you'll have to do some work to actually find it. But for several reasons to be showing up later, it's nice to just know at a glance if this converges or diverges. And so let's try to figure this out. So one case that we did last time and we'll just use, and the reason for isolating this, I'll point out in a second, is that for p equals 1, so if we just have 1 over x, last time we did the improper integral, we got this natural log, and that diverged. So this diverges. Because we checked it already, and we can go look at that if we want to remember how it worked. So then what happens if p isn't 1? So we can try to do this work, but what we'll have to deal with is the fact that we're going to try to do this no matter what p you actually have. But we have our procedure basically laid out here. Step one is, well, this is a limit. The limit as t goes to infinity, the integral from 1 to t, setting ourselves up for the next step, x to the minus p. The next thing is integrate. And right here, this is why I said think about p equals 1 separately. This is because as long as p isn't 1, you get to use the power rule. Whether the p is positive or negative or even 0, they all use the power rule, except p equals 1, that gives us the natural log. So there's a reason why this, we kind of say this is separate, otherwise we can use the power rule. And so what does the power rule look like? So we still have our limit. We increase the exponent by 1. And here we say, okay, well, I don't know exactly what it is, but it's whatever that number negative p is, I'm going to increase it by 1. And then I'm going to divide this by that new exponent, negative p plus 1. And I'm going to evaluate this from 1 up to t. And in here, there are these 3 letters around, so let's keep them straight. The x is the variable from the integral. That's where we're going to substitute in these 2 things. The t is the variable that we're eventually going to take the limit of. And p we're thinking of is, it's not really a variable, it's standing in for some fixed number. So it could be 2 or 1 or a half, whatever it might be. As it's written, it's not really easy to think about, well, we'll eventually take a limit of this, and it's not really clear what's going to happen. But if we rewrite this negative exponent here, if we factor out a negative, this is negative p minus 1. And actually, this negative p plus 1 is the same thing. So both of those, for the purposes of the simplifying we're going to do, kind of like we said, this expression, we'll rewrite it as a fraction that's a little bit easier to look at. These we can both rewrite as negative p minus 1. So if we evaluate, what we end up getting now, our limit is still around. If we put t in, we're going to get a negative 1 on the top. In this first case, it doesn't matter so much if we make this simplifying, but I'll write this negative p minus 1. And then writing this as a negative number, that lets us rewrite the expression like this. So writing it so it's a whole number with a negative in front of it, we can say instead of having this negative number and this negative exponent in the top, move that expression to the bottom and get rid of this 1 negative sign. So that's what happens if we put in t. If we put in 1, then this power is always going to be 1. So that doesn't matter so much, or that makes the top nice and simple. And we get 1 over p minus 1. if we're thinking of the bottom being like this, we're subtracting it from the second half of this definite integral, so the negatives end up canceling each other out. So then the question is, what's this limit? So the last part, as usually happens, is fixed. That we don't have to worry about. What we do need to decide is what happens to that first part with the t. And the split happens depending on if this exponent p minus 1 is positive or negative. It's never going to be 0 because we said p equals 1 is its own separate thing. But depending on if this is positive or negative, that really comes down to is p greater than 1, in which case we have a positive exponent down here, or is p less than 1, in which case we have a negative exponent down here. And what happens in these cases is if p is bigger than 1, we get a positive exponent down here. Our limit is something like this. We have a positive power of t in the bottom. And that means that positive power of t in the bottom is going to infinity, and the whole fraction is going to 0. And so if p is bigger than 1, this part goes to 0, and we're left with 1 over p minus 1. If p is less than 1, on the other hand, we're going to have a negative exponent in the bottom. So in this case, our limit would look something like 1 over 1/2 times t to the negative 1/2. So if you pick p equals 1/2, that's what you're taking the limit of. But if you have a negative exponent in the bottom, the way that you would do the algebra is say, well, move that to the top. So this is t to the 1/2 over 1/2. And if you have a power of t in the top of your fraction, that thing goes to infinity. And anytime the p that you started with is less than 1, at the last step where you have a limit, you have a power of t in the top of the fraction divided by some number, and that is always going to go to infinity because that positive power of, or that t with a positive exponent on the top of the fraction always goes to infinity. So this is infinity. So the takeaway here is this question, when does this converge or diverge? There's a very stark line, and it's at p equals 1. So this is our question. Then the answer is that the integral from 1 to infinity 1 over x to the p dx converges if p is greater than 1 and diverges if p is less than or equal to 1. And this is a fact that we'll just be able to use. If we ever need to know for an integral like this, does it converge or diverge, it all comes down to what's the p remember which way it goes, and then pick the right one. The way that I remember this, because remembering exactly which way it goes isn't the easiest thing to put together because they're very similar looking things, is what's easier to remember is one is the dividing line, for sure. One is the 1 over x is a sort of weird power of x, and so it's where things split. And then what you can remember is either, well, if this p was negative, then it's definitely going to diverge. That would be like finding the integral of x squared. And that definitely has an infinite amount of area. And so if you can remember, 1 is the dividing line, and the negative number, or the side that has negative numbers is where it diverges, that can make it easier to remember exactly how it goes. But as a tool, this is kind of nice because we can say really quickly, answer the questions, do these integrals, I'm going to write some of them, converge? And so this could be something like the integral from, let's say, 2 to infinity, 1 over the square root of x. And then also, let's say the integral of 1 to infinity, 3 over x to the 10⁹. So we have, do these things converge or diverge? And which of these converges and which one diverges? So there's one of each in here.
Second one converges.
So the second one converges, and the justification for this would be just this converges because the p you're looking at is 10⁹. One thing that doesn't affect convergence here is this 3 that's in the top. Like with integrals that we've encountered before, if you had a definite integral with a constant in it, you could factor that constant out, find it without the 3, and then take whatever answer you get and multiply the 3 back in. So this 3 won't affect convergence or divergence. Basically because if there's an extra 3 in here, you can factor it out of the integral and then factor it out of the limit, and it wouldn't affect whether it converges or diverges. In this first case, this is going to diverge, and while it's not presented exactly as x to the p, the square root of x, well, that is a power. That's p equals 1/2. So this one diverges. And the thing in this case, which doesn't really affect convergence or divergence, is the fact that we're starting at 2 rather than starting at 1. The difference between starting at 2 and 1 is this finite amount of area, the definite integral between 1 and 2, and whether you have that finite area or not isn't going to affect if this ends up being infinite or not. So this fact here, unless you're specifically asked to spot or to check that something like this converges the long way, we can just use this fact and we don't have to check it. Where you want to be careful though, a slight variation is if there is something that said, given, or in this kind of problem, if it said, identify if these converge or diverge, and if they converge, find the actual value, then what you need to do is say, okay, this one diverges because p is a half. This one converges because the exponent's 10/9. And since this one converges, I need to find the number, and that's where you actually have to evaluate the limit. So this fact gives us some information. Do you have a finite area or not? But it doesn't really tell us the finite area. Although, if you're starting at 1, it always ends up being this. But if there are extra constants or you start at different values, it might be different. So really, if you need to find the value, find the limit or the value of the improper integral, you really need to go through the whole process. It can be helpful to have a sort of graphical picture of what's going on. So I'm going to pull up some pictures of these. Some of these different graphs that we've looked at. So all of this type, but just comparing what these graphs look like. So the colors are coming in a little bit. Red and black are kind of close to each other. So in this picture, these are all the different graphs of these functions: 1 over x, 1 over square root of x, 1 over x cubed, x squared, and x to the 10⁹. And so all of these have the same basic shape. If I zoomed out, they all have, in the positive part at least, an asymptote at 0 and an asymptote at 1, or an asymptote at out to infinity. But what we can see here is that this exponent, and actually let me rewrite this one as x to the 1/2. What we can really see here is a little bit. So these are ordered in how big their exponent is. So 1 over x cubed, squared, 10⁹ to the first power, and then x to the 1/2. And if we look at these, as the power gets smaller, so green is on the very bottom here, 1 over x squared is the purple one just up from that, and then the black 1 over x to the 10⁹, 1 over x, and then 1 over x to the 1/2. So the power is really telling you how quickly these things decay as they get smaller. And in this case, it's not that surprising that 1 is this, or so we figured out that 1 over x diverged, we did that, but it's really, with the picture, maybe makes a lot of sense that things split the way they do. Because, let me, so this graph right here is 1 over x. No, wait. this top graph here, yeah, that's 1 over x. Yeah. And what we said about it is that this has an infinite amount of area beneath it. So we checked that the integral, the improper integral of 1 over x diverged. And this top one here is 1 over the square root of x, has even more area beneath it. So you can check either using the fact we just established or by hand that 1 over x is going to diverge, but graphically you'd say, well, if I checked that this one diverges and this has even more stuff, well, yeah, there's already an infinite amount of area below this red line here. This blue line has even more, so that should diverge too. But we can also kind of say the opposite way. So this line here is 1 over x squared. We just checked earlier today that this has its integral convergence. And if we note that that integral converges, and we look at the green line at the very bottom here, this is 1 over x cubed, that has even less area. So if there's already for sure a finite amount below this purple line, and we have even less, well, that better converge too. And we can check by taking the limit that it does, but also graphically, it makes a lot of sense that if you have a smaller thing, or if you have two things and the one that's bigger already converges, then the smaller one should converge. And if you have two things and the smaller one diverges, so the smaller one already gives you this infinite area, the bigger one, which has even more area beneath it, should diverge too. Okay, so finish writing. This thing has less area. So does everyone kind of get what I'm hinting, or what I'm sort of laying out here in terms of if we can compare the functions, like which one is bigger, we can sometimes get information about whether they converge or diverge. So a place where we want to be careful, though, is I've sort of labeled all of these. And a question we can ask is this, or we missed out on this one here. This is this bottom line of the two that are close together is 1 over x to the 10⁹. We can ask, what does it do? And we can check by taking the limit. But the thing that you need to watch out for is just from what we've labeled here, we can't really tell. Because we can say, well, this purple one converges, but this one has more area. Maybe it has enough that it diverges, so we can't really tell. And then we can say, well, it's less than this one here, this 1 over x. But that one has an infinite, that one diverges. So maybe this one is small enough that it converges. It doesn't have enough to get the infinite area. And so this picture, while in some cases, in some pairs, it helps us make sense of which things converge or diverge, it doesn't always work. Because in this case, we don't have the right comparison. But this idea here works in general. And after sort of laying out exactly what it is I'm saying here, we'll do an example where this comparison is actually really helpful, or this kind of comparison is really helpful. Last questions about this picture, or what it's all about before we turn off the projector. But we'll still be talking about this kind of comparison for a little bit. All right, so there's the remains of the projected stuff. So that comparison that I was laying out works in general. So what I mean is talking about comparisons of improper integrals. So the setting is that if two functions f and g are always positive, for x greater than or equal to a, and f is always bigger. Then there are two things we can say really corresponding to which of these converges and diverges. Then the first part is that if the integral from a to infinity of x converges. So this is saying if the bigger thing converges, all right, if the big thing converges, then the smaller thing converges. So that was one of the cases we said. We had 1 over x squared was bigger than 1 over x cubed. And if we knew that 1 over x squared converged, then the smaller thing would also converge. What we can also say is not exactly just, or we can't just flip converge and diverge here. What we can say is that if the smaller one, the integral of g, diverges, then the integral of the bigger one will also diverge. So we saw some examples of this in that graph, but it's also important to keep track of what this isn't saying. You can't always say, well, things like, if the big one diverges, you just can't really say anything. Because the thing that's smaller, maybe it's so small that it converges, but maybe it's smaller but still big enough that it diverges. And something like this can be really helpful if the integral you want to find is hard to really actually do the integral, but it looks like something that's really easy. So this would be really helpful in this case. So let's show the integral from 2 to infinity of 3 plus sine x over x dx. Let's show that this thing diverges. And we're not going to actually do an integral, which we're maybe thankful for, because this sine x over x, that would be, I don't know, maybe an integration by parts. if we're lucky and things work out, it's not really clear how we would integrate this. But what we can do is similar, it turns out, to like the squeeze theorem, not literally the squeeze theorem, but use some inequalities involving sine. So we know that sine is always between -1 and 1. If we add 3 to both sides, because there's this 3 plus sine x that appears in our integral, we get that 3 plus sine x is at most 4 and at least 2. So adding 3 to all parts of this, we get this inequality. And then divide all 3 parts of this by x. So 2 over x is less than or equal to 3 plus sine x over x is less than or equal to 4 over x. So now what we have is we have the function that we're trying to learn about in the middle of this inequality. And we don't use the squeeze theorem. That's not where we're going. What we want to say is, among there, we want to pick 2 of them to say one of them is bigger than the other one, and we want to use one of these facts. And so there are really 2 choices. Do we want to say, or do we think it's useful to say that this function is bigger than 2 over x? Or do we think it's going to be useful to say that this function is smaller than 4 over x? And here we really have to decide which of these inequalities actually helps us in this case. And how the decision goes is we'd say, well, 2 over x. Does this thing converge or diverge? And this question is actually much easier than what we were asking before, because this is one of those p integrals, the 1 over x to the p. In this case, we'd say this one diverges because the exponent, the power of x in the bottom, is 1, and that's, well, that's actually right in the middle, but it diverges. We can also really similarly say that 4 over x also diverges. So the integral from 2 to infinity of 4 over x also diverges from the same reason. So what we have to decide is it useful to know that our function is bigger than 2 over x, which diverges, or is it good to know that our function is smaller than 4 over x, which diverges? And the one of those which will be helpful is actually 2 over x. Because that combination is this second bullet point here. The second bullet point is saying if your function, if you have a big function f that's bigger than g, and you know the smaller thing already diverges, then the function f is going to diverge. And so if we can say here that putting it all together, that since 2 over x is smaller than the function we really want to learn about, 3 plus sine x over x, and the integral 2 over x dx diverges, by that second bullet point in the comparison, the integral from 2 to infinity of 3 plus sine x over x also diverges. So we can come to this conclusion that it diverges without actually doing the integral, which is good because it's really hard. What we do instead is say, if we compute some other or evaluate some other integral and see that it diverges, there's a way of taking that information and helping us, or helping us solve our problem by saying, if this happens for this integral, then it means something for our integral too. So what kind of questions are there? This is, very different from the ones we've been doing, which is write it as a limit, turn the crank, do the integral, do the limit, get the number or infinity out. But this is another way to solve these problems. There's really this kind of black box that you say, if you have the right ingredients, this tells you, given exactly what those ingredients are, here's the answer that you get. And what I think is especially weird about this is that really this part here, this is the final answer, and it's an English sentence with punctuation, and that's not really what a lot of math has looked like. So especially in kind of the third chunk of the course, which is sequence of the series, the content doesn't matter, but a lot of that is using some of these black boxes that say you check some conditions and then you get this conclusion, and the work is, or a big part of the work is explaining why this stuff helps us come up with this answer. Because none of these things here are actually explicitly checking that this diverges, but we want to say how, or that given these pieces, we're able to come to this conclusion. Okay. So we don't have a lot of time left, but before we really wrap up, are there more questions? I think the first type of question is, any of these specific things, like these inequalities or these integrals, why these are true? Just seeing, so understanding why these pieces are correct things to say is the first kind of question. And then there's the question of, well, how do we put them together? And maybe third level of questions is, well, how did you know these are the pieces that you needed to put together in here? And maybe as a point on that last kind of question is, this integral or this inequality here, this doesn't help, because what this is saying is that 3 plus sine x over x is smaller than something that diverges. So you can say this function is less than 4 over x, and 4 over x, that integral diverges, but those pieces don't help you learn about this integral. They just don't get assembled in the right way. You really want to say this inequality is true, and this integral diverges, and because this is the smaller of the two functions, the bigger one's also going to diverge. That's the combination that does help you say something about this function, which is what we really cared about from the very beginning. Okay. So what we're going to do next time is talk about this other type of integral. We've been doing integrals at infinity. We want to talk about integrals that run up against a vertical asymptote, where it's a lot of the similar ideas, but a slightly different setting. Okay. So I'll see some of you in lab today, or if not, on Friday. See you then.